Welcome to our Fall 2015 Senior Design Project. With the team of Cody Glass, Mark Bissey, and Rachel Bernick, we have designed the Performance Auto Shift System, also known as P.A.S.S. P.A.S.S is a bicycle shifting system that automatically controls a bicycle shifting. The goal of this project is to design a system that will provide enhanced performance and automatic shifting to a wide range of mechanical bicycle derailleurs. P.A.S.S manages shifting so that the bicycle is in the appropriate gearing at all times. It also provides ride data feedback to the user so that he or she can monitor and maintain a desired effort level. The P.A.S.S system is also designed to remain calibrated so that the shifting and riding data is accurate after initial calibration. To accomplish this project, we used both off-the-shelf as well as uniquely designed components.
The following includes our requirements and specifications for our design: motor unit capabilities, drivetrain power estimation, battery life, sensor calibrations, display unit, and system durability. The following questions were asked during our validation and testing plan. Is the motor strong enough to move a minimum of 8 pounds of force and fast enough to move the derailleur system similar to that of a manual shifting system? Can we attain consistent power estimation values? Can the battery last long enough under heavy, moderate, and light usage? Can the microcontroller ensure that the sensors are reading data correctly? Will the correct screens and information display when called to? And can the system withstand extreme weather and riding conditions?
The first step of the project was to design an electromechanical unit that would be strong enough to move the derailleur through its entire range of movement. Thus, we designed a subsystem that combines the mechanical advantage and backlash prevention of a simple lead screw and nut with the speed of a brushed DC motor.
The brain behind P.A.S.S is a teensy 3.1 microcontroller, chosen for its speed, size, large programmable memory capacity, and quantity of usable input-output pins. The teensy 3.1 is used to control the motor unit, drive the display, and process sensor data and user inputs. A variety of sensors are necessary for P.A.S.S to work. This included an accelerometer-magnometer combination chip, gyroscope chip, barometer chip, reed switch sensors, and a 10-turn potentiometer. These sensors were all run on a single I2C connection to the teensy microcontroller. To keep the user from overloading and damaging their drivetrain, a power estimation equation was necessary, which is the sum of the power of rolling resistance, wind, gravity, and acceleration. After riding the bike using the original mechanical shifting, we noted any erratic or troubled shifting and found the benchmark to be about 500 watts. A 1.8-inch TFT display was chosen for its readability in high and low light conditions, as well as its versatility for text and image sizing and color. The removable microSD card is used to provide static memory and store calibration values, user data, individual ride information, as well as bitmap images. To control the speed of the motor and shifting unit while still allowing enough current, pulse width modulation was necessary. Our carrier frequency was between 5 and 20 kHz.
As shown to the right, a reed switch is attached to the frame of the bicycle and a magnet is attached to a spoke. Every time the magnet passes by the reed switch, a 3.3-volt pulse is sent to the microcontroller. Timing these pulses allows us to calculate the speed in which the bicycle is traveling. Reed switches are used in our design to calculate the cadence of a bicycle. 2 reed switches were used to determine the direction of rotation of the tire and crank speed. 2 reed switches are attached to the bicycle, one in front of the pedal and one behind, and a magnet is attached to one of the pedal's arms. As the user pedals, each reed switch will be closed, sending a pulse to the microcontroller. The order in which these switches are closed will allow us to determine in which direction the user is pedaling. In order for shifting to occur, the user must be pedaling in a clockwise direction. All of our requirements and specifications were satisfied.